Testing. Okay. Before we get into ventilation, I want to talk about the gases and vapors lab. Answer any questions you guys have from that. Yeah. There is no standard for VOCs. Yes. So there are some organizations that recommend a sort of limit to VOCs of 10 parts per million. 10 parts per million. But, you know, I don't know how worthwhile their recommendations are. So for all the lab reports up until gases and vapors, you have had a reference from which to compare your results. With gases and vapors, we don't necessarily, because there is none. If you want to use that guideline of 10 parts per million, then that's fine. The goal of the gases and vapors lab is to simply understand the distribution of the gases and vapors in the lab. So how are the gas and vapors emitted from the printers being distributed throughout the lab in that one little snapshot in time? So obviously it's going to be different depending on the day and what printers are going, but that's the objective of that lab. That lab is to just understand distribution. So there is no reference of the gases and vapors of the VOCs that we measured. Let me write these before I forget them. So the gases and vapors lab, we'll go over the exam. We're not going to review all of it because of time, but I will cover at least the two. There were two questions that more than half of you missed. So we'll definitely cover those. And there will be some curving that goes on. I haven't decided exactly how to do that, because in the past I would just go with the questions that most people missed. But because there are only two of those, that won't help a whole lot. So I'm going to be curving, but I'm still trying to decide how to do that. Anyway, all right. So gas, yes.
I'm having a hard time understanding how you just want us to say understand the distribution of the VOCs.
So you're making a little map of the VOCs. Now, this type of distribution map is I might have said that it's it's typically used for noise, because it is, at least in my experience, but understanding dispersion of contaminants is important for industrial hygiene. I know, for example, at the mine I worked at, they had a chlorine tank because they used chlorine as part of the process. It was important to understand if there was a leak in the chlorine tank, or say a rupture or something, where is that chlorine gas going to go? And so they did, this was before I got there, but they did a dispersion study. So they had multiple people standing around, just spread out all over. And obviously it's affected heavily by the wind that happens to be, present at that day, whatever the direction is. But anyway, they release a tracer, not chlorine, a tracer gas, and then everyone at their position measures it. And when you're done, then you have a little map of how that gas was dispersed in the air. So we're doing that, but just for the 3D printing lab. So you can use there is software that is fancier and will look nicer than Excel, but don't feel like you need to use anything fancier than Excel. You'll be entering your numbers in parts per million, and I'm just making stuff up right now. This is higher than what it really was. And I'm just gonna do a smaller area. Oh, that's not what I meant.
So we're going to make that table for the
You're gonna make a little map.
for the
Yes, for your report. And so it might look something like this. And then let's just go small here. And I mean, with Excel, you just, it's nice to have the numbers in the middle because they're more visible. And then use the conditional formatting and the color scales. And we want to flip that because low is good. So you'll have a little map that looks something like that. And what I would like is, I mean, obviously it'll be bigger. Just create something that tells me where, for example, the table that the students sit at is. Where is it? So you could, on top of this, have a little box drawn or something that shows, okay, this is where the table is. This is where the door is. This is where the printers are. Basic things like that. Basic landmarks. Questions?
okay.
Okay.
I'm not good with this Excel here. But
Okay.
how are we going to draw a map there? Just
Well, you could do it in Excel or in Word. Just insert a, let's see here. Maybe, oh, here we go. I'm just not seeing. But anyway, you're going to insert a shape or an object. I forget what it calls it. And then just draw it. And you want to take out the fill so you can see beneath it. You'll maybe make the outline a little bit thicker. So just, it doesn't have to be super fancy. It'll be a bit bigger, but have like the table and the door and the printers where that stuff is. And I think which some of you were kind of noticing, it seems like with the conditions that were present on the day we went, the table is it has one of the higher, it had some of the higher concentrations, that area compared to other spots, which is interesting. Other questions? So you will now have a reference. Just talk about the distribution. You could use some basic descriptive statistics. What is the average? What is the geometric mean? I think you'll see that I haven't I don't even have the data, but if you were to look at a histogram of those data, and if someone has done this, then you can help me confirm or validate, but you'll probably see a log normal distribution because there was a lot of 0.1, 0.2 away from the printers. As we moved away from the printers, there were a lot of low exposure levels. So geometric mean might be better to use than the average if you're going to use some. And then the 5-number summary, so maybe a minimum, first quartile, the median, etc., rather than using the arithmetic average or a standard deviation. Other questions? So I need to post some slides shared by one of your classmates, Kasim, about 3D printers. Just be able to describe how they work. Basically, that they have a filament, and we talked about the two filaments, PLA and ABS, that gets heated in the little nozzle and then extruded onto the model. And in that process, it is vaporized, basically. I mean, so it evaporates. Plastic compounds are evaporating into the air and diffusing throughout the room. So if you can find anything related to potential health effects of exposure to PLA or ABS, now you won't find it for those specifically necessarily, because when you heat compounds, they may change chemically. So that's a difference from an aerosol can, like we were doing before. There may be some chemical reaction going on there, but not likely. Or if it is, not very much. When you heat stuff, there's interaction and it's going to change. So if we actually measured everything that was in the air, which for Drew's capstone, we didn't find PLA or ABS in the air. It's a bunch of other stuff, a bunch of different VOCs. That's what's in the air. So you'll want to talk a little bit about ABS and PLA, talk a little bit about health effects from VOCs, and see, well, and that might be useful if, for example, students in the lab start to complain about some of those things. They align with their exposures, and we start to think maybe they are being overexposed to some of these things.
What are the vapors in that lab? What chemicals?
What do you mean?
Well, like
That we were measuring, or
yeah.
if you would like, I can share with you Drew's capstone, at least the draft. Still working on revising it and getting it ready to publish, but I can share with you that, and you'll see the data. Basically what you want to look for. You don't necessarily need to look at it if you don't want to, but there's something called the TO canister. That's what we use to identify what sort of compounds were in the air. It tells you what's there, and it tells you the concentration that was collected in the little can, but it's not an exposure concentration.
Are there specific chemicals in that lab that we have to be aware of and check on?
If there is anything specific, it would be whatever you see from the TO canister. Don't feel like you have to, though. You can just talk about VOCs in general. Talk about potential health effects from just VOCs in general. Or if you find any legitimate source that talks about health effects from 3D printing VOCs, then you could talk about those. NIOSH has been interested in 3D printers recently, and they do have some information. They have studies. I'm not sure how much they have on their website, but that would be a legitimate source to turn to for VOC health effects in general.
Some of them are really hazardous.
Yeah, there's nasty stuff.
Nylon, especially when you get in there 3D printing and sintering.
Interesting. From Drew's TO canister, there wasn't a lot of interesting stuff. I mean, some typical things. I can't remember what they were, but there wasn't a ton that was super alarming or super concerning. But yeah, and every time we took samples in there, like a little while later, they're telling us that they're getting new printers. Like there's new additive printers coming out all the time. And it's like engineers, who say, there's an engineer who runs the lab. They're like, oh, it's something shiny and like a cool toy. And that's how I look at it too. But a lot of times we don't think about, well, what the emissions from this thing as well, what could it do to health? And so you know, that is not uncommon for other 3D printing labs around the country, is just like adding more and more. Wow, these are cool. Let's add more. Let's add this new model, this type of printing. So that's not uncommon. So in your discussion, what do you think you're going to be talking about? About maybe why the distribution pattern is the way it is. So we also talked about the location of the supply airs plus the return air was kind of down here in the corner. And the door, if people are coming in and out, there's going to be some sort of informal, ventilation and dispersion created from that. So just talk briefly about why you think it's moving the way it is in the room. And recommendations, what do you think you might have? Now, none of the levels were super high, so it's not extremely concerning. Well, again, there's not a standard or a real good reference for VOCs. So, there is a sort of rule of thumb of 10 parts per million, but that is, I'm not even sure it's like a governmental, or I guess like ACGIH is not from the government, but not like a professional national organization that came up with that number. I can't remember who came up with that number, but anyway, so I don't know how much weight to give it, but it seems like a reasonable number to me, 10 parts per million. So the numbers weren't super high, but you could just think about the general things that you want to do to increase the general ventilation in there, right? Or, well, so first let's talk about that. Kind of a similar idea with our bioaerosols and indoor air quality. So what might you do to just increase the dilution that happens in here? Good. So, okay. So for general dilution ventilation, increase how much the system comes on. So more fan time, whether it's actually conditioning the air or not, supplying more clean air to the room, making sure the door is open often, that would help. And then also, so to Steve's point, you could have local exhaust ventilation, meaning you enclose those maker bots. So the big ones are already enclosed, but I don't know if they have exhaust ventilation, so that once the tech opens it up, they might get a nice, waft of ABS products. I'm not sure if it's ventilated. It may have for example, a filter inside. That's my guess. Is those big ABS printers have, it routes the air through a filter and then puts it back in. But yeah.
Can we use like this doors, like with the ventilation, so there's no exposure to the wood?
Sorry, say that again.
So the 3D printer with fixed doors, you can close it and there's ventilation source.
Yeah, so a good option would be to enclose each printer and then have an exhaust ventilation system connected to it. And most of the manufacturers include an option to have that stuff. It probably doubles the cost. Yeah, of those little ones, it's probably double the cost. But it's something to consider. You wouldn't have to get something fancy though. You could probably, like AxFab, students in AxFab could probably manufacture some simple plexiglass enclosure with a door. It may not have ventilation, but it wouldn't be a high dollar intervention. It'd be pretty simple, I think. Other thoughts or questions? Yeah.
Possible to have like sensors for that kind of type of paper or whatever.
High-end ones too, like the laser printers. Discussing
Yeah. I mean, it's possible. But again, it's a matter of cost. And for those little ones, I think they figure that the exposure isn't going to be that high to justify the, you know, the sensor. But just like what happens with most 3D printing labs or rooms or whatever, it starts with 1 or 2, and then they're like, wow, this is awesome. Let's get 10. And then, you know, 10 is different, but other thoughts or questions? Yeah.
What's it called again?
General dilution or general ventilation or dilution ventilation would be just your supply, just pumping more clean air into the room. Exhaust ventilation means you're pulling the bad air out, which, so yeah, we're going to talk about that today. But before we get to that, let's talk about, for sure, we'll talk about, where are we? These 2 questions. So this was probably the most involved question, I think. And most people were on the right track, but I think you forgot one conversion, maybe. That's my guess. I purposely worked out the conversion error and put it as an option. I'm sorry.
What question is this?
It's got to be like 6 or 7 or 8, maybe. It doesn't mark it on here, I don't think. Maybe it's 5. Go with that. The options are 12, 11,000, 13,000, and 14. So we're reasonably confident that we will collect enough hex chrome that will get detection, but we want to make sure we don't overload the filter. So we, last week, we looked at the method and we saw that they said, don't, you know, collect less than 1 milligram of dust. You don't want more than 1 milligram. So we knew that that was our upper limit for our collection mass. So that was in sampling section on page 2 of the method. And it indicates, number 2 indicates an upper limit of mass for total dust loading on the filter, which is 1 milligram. So our mass is going to be 1 milligram. What will, or I'm getting ahead of myself here. What will the mass of our sample be, assuming the estimated concentration is accurate? I'm getting ahead of myself. And then how does that compare? I guess, so our upper limit, I don't know what to call that, mass is 1 milligram. But we just want to know how much mass will we collect if we use the parameters that we've already decided on. 400 minutes and a flow rate of 1 liter per minute. And let's say that we were really good in guessing at what the concentration actually is. And it actually is 29 milligrams per cubic meter.
Not milligram.
Micro, sorry, thank you. So the same 2 equations, concentration equals mass over volume, volume equals flow by time. And our target is the mass. We want to know what our mass is, and then we need to compare it to our upper limit, which was 1. So we're after this. I'm going to just go ahead and plug that in here. So we have concentration is mass over flow times time. If we just multiply by QT, not the gas station, then I have my wife's uncle loves QT. He has like an obsession with QT. Anyway, are there any QTs in this area? Quick Trip. Yeah, Quick Trip. Yeah. Anyway, he's a larger guy, but he has a it's like a ritual. I don't know, to get a large soda from QT. Anyway, so we end up with, if we were to abbreviate this, it would have been concentration by volume, but this is how we're going to get our volume. So we have our concentration times our flow times our time. And I'm going to use my little line just to watch the units to make sure they work out the way I want them to. So we have 29 micrograms per cubic meter for concentration. We have a flow of 1, is that what we decide on? 1 liter per minute? Per minute. And we have time that is 400 minutes. So we're sort of maxing out the volume that they gave. They gave a range of, what was the lower range? I think it was like 34 liters up to 400, or 8 to 400. Okay, I was wrong. 8 to 400 liters. It's generally good to try and hit the volume on the high side. So that's why I chose these. Is you want to try and, if you go over a little bit, it's not really, this is just something practical. If you go over on the volume range, it's probably not that big of a deal, as long as you're not overloading your filter or something. Having extra air is okay. So I'm looking here, my minutes are going to cancel out. I'm looking for a mass, so I just want this. And I see I have these two volumes, but they need to cancel out, and they can't the way they are. So to do that, I'm going to say 1 cubic meter is 1,000 liters. So my liters cancel, my cubic meters cancel, and then I'm left with this number, which I'm not going to try and do in my head, but I'll wait for you guys. You'll be faster than me with this. That's going to be around 1,200. 11.6. So this is 11,600, but then you have to divide by 1,000 to get the units to work out properly.
That is divided by that.
Right. So the correct answer is 11.6, or about 12.
But the bottom one, what?
So why is it that the answer is 11.6 and the correct answer is now 12?
I did round up.
But what?
We have 11.6.
No, that's
No,
that's 11
because it's the other one is yes,
11,600 micrograms or 11.6 milligrams.
Which is the correct answer?
It's my.
Is that the right answer?
11.6 micrograms.
It's 11.6 micrograms. So maybe I confused you with this. I was trying to clarify, to point out that I'm talking about, well, I mean, I was trying to clarify with that. Maybe it made it more confusing.
Yeah.
All right.
If you're looking at that and you're going the right
And you see this answer, yeah.
The right answer's not there. And then I was like, it's 11.6 micrograms. And then it's like 11.6 isn't up there. We must have rounded up to 12, so that's what I picked.
So yeah, so I appreciate the feedback. Like, so my policy is to make questions that more than half the class misses worth 0, so that it's not going to count against you, right? Then you'll still benefit, and there will be some additional curving because it's just the 2, but that's the process for that one. And I apologize. I thought that extra information would help. Maybe I should have just highlighted the units rather than, make the conversion also there. So the next one was the only other one where over half missed. You're prepared to take, you prepare to, and then take a sample I need a comma there. On a primer and paint crew member for hexchrome, your pre-calibration flow rate is 1. So our pre-flow is 1.005 liters per minute. And our post, I know the information isn't in this order, but our post is 0.994 liters per minute. We have a sampling time of 385 minutes. And the laboratory, so this could happen if, I don't know, you have a weird laboratory or you forget to give them the volume. Then they won't give you a concentration. They'll just tell you the mass, and you've got to calculate the concentration. So we need our concentration, and then we need to convert it into a time-weighted average. So first, concentration is mass over volume, but I know that volume is the same thing as flow multiplied by time. So I find the average flow here, and I believe it's like 0.9999995. All right. So I am just going to plug all these numbers in here, and I'm going to do my line just to be sure that my units are right. So a mass of 16 micrograms divided by a flow of 0.9995 liters per minute. Also divided by our time, which is 385 minutes. So I see my minutes are going to cancel. And this is how I want it, a mass on top and a volume on bottom, but not in liters. I need it in cubic meters. So I'm going to convert that. So my liters cancel, and I'm just left with micrograms per cubic meter. We'll just leave it there for now because we see the answer options are in that. So doing that gives me, I'm trying to remember the number. I mean, I can pull it up, but could somebody help me out here? It's going to be
42 micrograms. Or it's 42 micrograms.
42.
Why are we doing these time and not this?
For the time weighted average, we use 480. So the concentration of our sample is 41.6 micrograms per cubic meter, but that wasn't for a full 8 hours. To time weight it, then we take this number. So it's the concentration multiplied by the time of our sample divided by the 480 minutes. You know, and these minutes would cancel out. So this is basically just a ratio multiplied by our number, and that lowers it down to about 33. This one was also a bit of a multi-step process, like the other question we just did. So they were probably a little more time consuming. So other questions on the exam? Again, I will remove the point value of these two questions, and then I am going to do some curving after that as well.
So on the all that dust, if you look on OSHA's site, the restable dust, the correct answer is different than what you call.
What does OSHA say? for respirable
as well as thoracic.
as well as thoracic.
Because this one's actually, it's actually 6 to 4, something like that. It's in between.
So that's interesting that they say that. So inhalable is, I mean, maybe I didn't say give a range in class, but it's less than 10 microns. Respirable, there are different numbers used, either 2.5 or 4, depending on who you ask. But respirable is less than one of those, either 4 or 2.5. And then ultrafine is really small. Yeah.
Question on number 4, or question 4 about the volume.
So
So on
which,
question 3, it says that you want to assume that you're using the highest flow rate of possible, which if you look at the CD or the process for hexavalent chromium, it gives the flow rate of 1 to 4 liters per minute. So we're assuming we're using a flow rate of 4 liters per minute. Then the question asks, given that the volume is insufficient to reach a method's recommended range, what's the minimum sampling time to reach the minimum required? Well, sampling at a rate of 4 liters per minute and the minimum volume is 8 liters. The minimum sampling time should be 2 minutes.
so that 8 liters number is, I'm not remembering it. Let me pull it up real quick to see. Let's see, what is it? It's right here. Okay, cool.
Sorry. Can I
No worries.
show you this on the computer?
Yeah. Okay, interesting.
So how do we have to look
So that's a different version. I probably should have provided it for you guys.
I Googled it.
And that's what came up. Okay.
So,
Okay.
Did you pull up the 800?
so my numbers don't match your numbers.
Right.
Then you do the same?
Right.
And which one is this?
Number 4.
Yeah.
Yeah. So I should have just provided it for you. So we can, well, we'll see how much curving has to be done after we make these adjustments, but we'll, for those who missed it, I'll just give it to you for that one.
Because it just said the NIOSH process 7600.
Right.
So I just Googled NIOSH 7600 and clicked on the first
I have a
result
few,
that came up.
Right. So I should have either been more specific or just provided it for you there.
That's what I had to.
So what am I looking at? Why is
It's an older version. So the very first version was published 1989. The most recent one is 2015. So I should have specified that, or again, provided you with the actual document.
Okay. So then the math doesn't work. 'Cause the
Right.
values are different.
Right. So yeah. So I'll give it to everybody who missed that one. Other questions? No more questions on the exam?
The last question.
Let's see. This one? What's your question?
I thought from the slides, that was like a medium line, so a lot, nothing.
Well, so it does look weird because you have letters here, What that means is they were not able to detect a mass on their own blank, but they did detect something on your blank. So you would want to see non-detect here and a number here if the lab messed up. That means somehow they got, I didn't say what it is. Let's say it's silica. Somehow they got silica containing dust on the sample. If this had a number, that means they actually measured some silica on their own blank. But because it's on yours, then you messed up. You'd hope to see non-detect on both of them. That's what you would ideally see there. Other questions? All right, so there'll be 3 questions that, 2 that I will remove the point value for. So if you got those right, you get bonus. Maybe we'll just treat all 3 the same way. And then after that, I will do some curving to the exam. I just don't know exactly how much. I want to see what the numbers look like after I do that. All right, let's go to ventilation. So far, we've been talking about measuring exposures, and when we talk about heat, and we'll have 2 more exposure labs with noise at the wastewater treatment plant and heat, which we're just going to do that's going to be another one where we just sort of, if we wanted to do it for real, we'd have some equipment that I don't have. Ingestible thermometer, and yeah, I mean, I've used those, but I don't have them here. And then what's called the WBGT monitor. So we'll talk about that when we get there, but it will be more of a hypothetical situation for our lab when we do that. For noise, it will be the real deal. We'll be at the wastewater treatment plant and see what their employees are exposed to. For ventilation, though, we are assessing or evaluating a control. So this is a control measure, not an exposure that we're evaluating. And I do have some pictures, so I'm gonna make sure lights are off. With indoor air quality, I think we think a lot of dilution or general ventilation. When we think of high risk exposures that are airborne, then you usually want to think of something like local exhaust ventilation. So what are these guys doing? They're welding. So there's a sort of point source generation of a contaminant, and it's a contaminant that is highly toxic. It's very hazardous. And so you don't necessarily want to try to use dilution ventilation in this case. It's not going to be that effective because it's a little point source. If you just are able to exhaust the contaminants at the source, then you'll be much more effective at protecting people's health. Now this, do you notice anything wrong with this picture? Maybe just looking at, I mean, look at, you could, well, it doesn't look like maybe it's in a bathroom. Yeah, that's a good point. I hadn't thought about that, but that is concerning. If these ventilation systems were on, what do you think you'd see that you don't see? Yeah, exactly. So it's still kind of just, it's moving right for him. And I don't really see these fumes moving in this direction here either. So I don't know, either they're not on or they're just not very effective. Now, one, you don't have to be a ventilation engineer to just get a quick sense for how well a ventilation system is working. We were doing some volunteer work for an industrial paper shredding operation in Tucson that employs handicapped people. So they had people with different mental and physical disabilities. There were some people who were deaf, and there was even a guy who was blind, and they had jobs for him. And the blind guy actually worked in the paper shredding area. Anyway, they were concerned about noise and dust in that part of the facility. And one of my professors was with us, and we didn't have this piece of equipment, which is what we would have liked to have had. We didn't have it with us. He just tore off a little shred of paper, and then he was holding it near, now the systems didn't look like this, but near the hoods, ventilation hoods, just to see, is it actually, getting sucked in or not? And, I mean, there's some things to look for. You don't have to have tons of fancy equipment to know that it's not working or to know that it is working. It's kind of in between where it's hard to know, but you can generally tell if it's not working at all or just very poorly, then you can usually tell. And if it is working well, you can usually tell. So our objectives there, just discuss basic principles of industrial ventilation, talk about some components of a ventilation system, and then look at some equations. We are not going to cover all the equations that are in these slides. Some of them are review, so we've already done air changes, but we are going to look at, and we've also looked at flow. We'll review that one though, because it's important. Mostly dilution. If there is time, then we may look at capture velocity. Think of air. Now, I can't remember if I've mentioned this in this class, but gases and air behave like fluids. I haven't had an entire fluid dynamics course before, but I had one that was about half of it seemed to be fluid dynamics. Air and gases behave like a fluid. They have more energy. They're less bound by things like gravity, for example, than fluids are. And if you imagine air moving, I want to explain this, this figure here, moving through a pipe like a duct. It can either be moving nice and smoothly, or it can be very turbulent. So this is what you do not want in your air system. You want nice, smooth flow. And we'll talk about some things that contribute to both of these later on. But with ventilation, you want to either dilute or remove the contaminants. It also is for comfort. So we heat and cool the air. We may even either add or take away moisture from the air. In Arizona, we probably more likely want to add moisture to the air. In South Florida, or I don't know, I mean, just in the South, maybe you want to desiccate or you want to dry the air. Also, we don't really talk about this in this class, but there's something called combustible dust. Can somebody just, okay, so what happens at like a flour mill?
Ultrafine dust and accelerant, so it creates an explosion. The same equivalent of dynamite.
Yeah.
Facility. That's what they have. Their air movement systems inside of those facilities.
So about 10, maybe more than 10 years ago now, I think it was in Georgia, there was a sugar refinery that blew up. That basically maybe not 100%, but a large portion of the refinery blew up, and it's because they had so much sugar in the air. Just about any dust, I don't want to say every dust, but most dusts will explode if they're found at the right concentrations in air. And the finer they are, generally the more combustible they are. So that's something to think about. We're not really going to talk about it in this class, but like, so flour, grain, sugar, those are some of the common ones, but anything, metal dusts are extra explosive and flammable. So you have to try if you get powdered sugar, if you want, well, maybe I shouldn't encourage this, but I'm not encouraging this, but but it is possible to like throw powdered sugar in the air and then light it, and you just like any sort of like an aerosol can or something. Yeah. Yes.
You throw coffee,
Or creamer. Yeah.
coffee creamer, the powder one, in a fire, it just like explodes like Harry Potter.
So
Crazy.
maybe what I'll suggest is look on YouTube. Don't do it yourself.
That's
um,
interesting.
Unless you're a trained professional.
So this is just like the butter bakery, right?
That was for gases and vapors.
Yeah,
But-
it's the same with fine. No. Okay.
I'm not sure I understand your question. I think it's something different that you're thinking of. So we talked about general dilution. There's HVAC, which is general. If it's in an indoor air quality sort of situation, it's diluting the CO2 and hopefully removing it as well. I mean, we've got a return air. I don't know how well it works, but dilution is good when you have, so you have lots of point sources or just big general sources. So a bunch of us breathing CO2, you don't have a little exhaust ventilation for each of us. And we're also mobile, so that doesn't help. And then there's natural. So like with the particulate lab, just doing it outdoors and letting the natural air movement dilute your contaminants. This is so these are some different components or the different types of ventilation and sort of examples. This is a door. It's kind of hard to see that, but this blue thing on the left side is a door that's open. This is a fume hood. That might be a misnomer depending on what they're generating, but so this is a fume hood. This is like a supply air vent, and this is a fan. We'll say it is pushing in air from outside. Like, so there is no wall behind these blades. It's open on to the outside of the world. So of the four types that we talked about, let's start with this one. So what type of ventilation would this be? D. Good. So that is local exhaust. See if I can. Oh, okay. I don't have these, so I can click on them. So I think it's going to go in order. So general or natural ventilation would just be from outside coming in. What about this B? What do you think from the fan? Sorry? It is ventilation. What, huh? Well, so C will be HVAC. It would also be a type of general dilution ventilation, but it's more active, I guess you could say. Whereas here, we're trying to, it's just the natural air movement. Huh?
Which one are you talking about? Is it pollution?
This.
Okay, the fan.
Yeah. So there is general ventilation that would be natural, like on the last slide. It's just the natural air movement from the wind or whatever. We could also have dilution ventilation from something like a fan or an HVAC system. And then local exhaust. There is one issue with this local exhaust ventilation system. What do you think? Might be wrong there.
Where's it going?
Okay, well,
Go back again from the
So it is far away from the source. You know, it would be what would be ideal. And the other point that I want to bring up is if this person is required to do any work in this space, it's pulling the contaminants across their face into their breathing. So what you would want is slots around the top of this that just suck it right off the top. You could even, I mean, if it has to be open, then that's what I'd do. If not, then just cover that thing so it's not emitted at all. Anyway, so like with the popcorn lung, the diacetyl, that's what they did is the vats didn't have to be open, and maybe they slightly changed their process, but they just covered them all, and that did the trick. No more popcorn lung. There are a couple of types of velocity that we'll talk about: phase and transport velocity. The type that we're going to measure later today at the chemistry lab is a face velocity. So that is the velocity of the air at the face of a hood. So some hoods look kind of like this would be a slot hood. That's just, you know, capturing contaminant and sucking it in. The face is this part right here. Or if you have never seen a chemical fume hood, you will see it today. But there's usually like a sash and these little sliding glass doors, and you have your well, that's a bad beaker, but you have your flasks and your beakers with chemicals that you're working with down here, and the face is this part that's open right here, open to the outside where things are getting, air is moving in to the system. Make sense? Do you have a question, April?
I guess I don't understand the second one you drew. Is it open?
So this was the sash. There's like a sliding, I don't know if it's glass always. It could be like plexiglass or some sort of clear plastic. But so there's this sash that you can move up and down depending on how much room you need to work in there. So that's what this is.
Mixing in there?
Yes. So ideally, you know, if your elbow height is right here, then this sash should probably be down, you know, more like that. But whatever is open, that is the face. So when we talk about face velocity, we're talking about the velocity of the air at this point. Yeah.
Why not put a circle, like, you know, the babies when they're born, just put the gloves in there?
What's it called?
A hole in them.
A glove cabinet. I'm not sure if that's the official term, but
Yeah, but why not just like put it there instead of sliding it up?
well,
it will still be-
I think there may be two reasons. One is if at a certain level of toxicity or a hazard, if the hazard is high enough, then yeah, you'll want a glove cabinet. So like if you've ever seen in the semiconductor industry, it's partly to protect the worker, partly to protect the product. But instead of a clean room, if there's a smaller process, then they'll have a box with glove holes where you stick your hands in, and then you can do work and you can see what you're doing, but it's all enclosed. Or like gunsmithing, which is common around here. If you're doing a special type of spraying on your parts or something, or for like sandblasting, sometimes you'll have a glove box you stick your hands in. So that's what Maria's talking about. So that would be a higher level of protection. But for these chemicals, maybe that's not necessary. It also is more convenient than a glove box. So if the hazard isn't high enough to justify it, then you probably opt for this for the convenience of it. Then the other type we'll talk about, though you won't really use it outside of this lecture, is transport velocity. So that is the velocity required to maintain the contaminants in the airstream. So after let's say someone's sawing sawing wood, and we have a local exhaust ventilation system, and it's capturing the sawdust as it comes off there. And we have a ventilation system that takes it outside to a dust collector or something. There's a certain amount of there's a minimum air velocity required to keep those sawdust particles in the air and moving, so that we don't get them into our duct and then they kind of settle out. They'll settle out of the air. And that's a common problem with like carpentry shops, is if you like cut the duct in half and you look in there, there's like a bunch of sawdust in the duct, lining the whole thing. And that's also a combustible dust problem, having all that stuff lying around. Anyway, so you have to maintain a certain velocity to make sure that does not happen. You don't get a bunch of dust buildup in your duct. It happens in HVAC systems too. I know some people, there'll be lots of dust in their ducts at home, and they'll want to like scrub it all and just have it clean. Maybe although I've heard that you just should leave it because if you like try to clean it all, it just disturbs. You won't get it all, and it disturbs a bunch of it, and so you end up with more dust in your home air than if you had just left it. I don't know if that's true, but okay, one final type of velocity is the capture velocity. We'll look at a figure that describes the type of velocity required to capture different types of particles. But real quick, what do you think? Let's say we have sawdust, and then we have the VOCs coming off the 3D printers. Which one is going to require more velocity, a higher air velocity to actually capture it and get it in the system? Sawdust. Why? So it's larger. Yes, it's larger and it takes more to capture it. Don't worry about memorizing this or anything. It's just to demonstrate that idea. So a solvent, or like a VOC, for example, gases and vapors. And these are just general ranges. It's not like these are hard and fast numbers, but you can usually capture it with 60 to 100 feet per minute. If you have welding fumes, you're getting a little bit larger, but they're still pretty fine, pretty small, 100 to 200 feet per minute. Crushing, so think of just basic dusts, or if you're like spray painting. And then the final is cutting, blasting, grinding. So like carpentry, if you might be doing cutting with a torch or something, and the key difference there is that as you cut, you're generating, the material that you cut off is being generated and aerosolized. Abrasive blasting, is anyone who could describe abrasive blasting to us? Okay, sandblasting. So what for someone who doesn't know what it is?
So you're doing is you're taking an item, let's say a painted panel, and you're removing the paint to get down to the metal. You're using an abrasive, anything from a silicon carbide to just pure silica to silica mixed with something else. And it's this heavyweight bead that is forced through a nozzle onto something at a high velocity to remove the paint while still maintaining the metal finish and not damage.
And take home is it generates a lot of dust and stuff. Yeah, or if you're doing larger scale, well, you saw the picture of the guys who were putting primer and paint onto the aircraft. And so I imagine like you're sandblasting an aircraft. They're going to still be dressed in a similar manner. They're going to be like full suit, basically, because there's going to be so much particulate. Probably. I haven't seen those, but like a vacuum. I would hope so. They probably do. So that would be the ideal, is to be able to exhaust all the, so you said pure silica. So it's like, it's not good for their silica exposures. you would hope to be able to vacuum it off as soon as it does its job and then pull it out. Or there are sandblasting chambers, which like I wasn't familiar with sandblasting chambers the first time I walked into one, but I was just shocked at how sort of rudimentary the controls were. They had like a little hose with a hood respirator, and the guys just go in there and they sandblast stuff, and in a big box. So like cut this room into thirds, and it's like this big metal chamber about the size of a third of this room. You go in, and they had these really large molds that they were trying to make a sort of like a matte finish on. So it's a metal mold, and so they sandblast it with. They have different stuff too. They had like glass beads and can't remember what else. But anyway, it makes this nice kind of matte look on the mold. It was interesting. I'd never considered how they make that, and that's how they did it. So transport velocities for gases, like you'll non-condensing. So it's not going to condense on the sides of your duct and like settle out. It could be, I mean, very, very low air velocities. So, 1 foot per minute may be sufficient. So like the VOCs at the 3D printing lab, it doesn't have to be an intense system to transport it. As long as any of the air is moving in the right direction, then the rest of it's going to kind of go with it.
Can you give an example of a gas that does that?
Condensing? I don't know of one, but think of something where the boiling temperature is really, really, really low. Okay, so carbon monoxide. So carbon monoxide is not going to condense, and maybe in Antarctica. I don't know where it condenses, where it goes from gas to liquid, but it would have to be so cold that like the gas probably isn't your biggest concern. So some gases, just for them to go from a gas to a liquid or liquid to frozen, the temperatures are so low it's just not realistic that you'll ever see it. So carbon monoxide is a good example. It's not going to happen. So like you could have really low flow rates here and you're going to be fine if that's all you're trying to transport. Vapors, smoke, and fumes, it jumps up here. It's a 2,000 light or medium density dusts. So sawdust or plastic dust are examples. 3,000 feet per minute, and then other dusts like wood shavings, silica. I imagine these are larger dust particles, grinding dusts at 4,000. So that's pretty high. Up to 4,000 feet per minute is pretty high. Basic components of a local exhaust ventilation system: you have the hood where you capture the contaminant, ductwork that helps you transport it wherever it's going. Usually before it reaches the fan, you have some sort of air cleaning system. We're not going to really talk about those. Maybe we should, but there's cyclones are one. We talked about sampling cyclones, but on a dust collector, sometimes you have an industrial-sized cyclone. Those are good for getting large particles out of your airstream. So they'll be good for that, not for the smaller particles. Another is a bag house. Basically, what you have, well, let me see if I can find a picture of one. I think it's helpful just to see. I was hoping to see inside one. This might be inside. Yeah. Let me make that big. Maybe. Can we do that? Okay. So it looks like they have doors that they've opened up on this. This looks like a typical back house, dusty inside. So what you have is inside these are called a sock. Inside the sock is a little wire frame that just helps it maintain its shape. And what's happening is, I'm not sure which way the air is coming in. It kind of looks like maybe it's coming down. So let's say, because I don't see duct work up here. So let's say you'll have duct work down here where that's leading to the fan and the fan is pulling. So the air that enters here, you'll have other ducts that lead into here, and there's a bunch of dust. The air gets pulled into the sock and then down and out. And as it does, the sock filters out the dust. So the dust starts to accumulate and load onto the outside of the sock. It's really dusty. Huh?
How does that go away?
Someone has to clean it. So that's a dusty job. Huh?
The same concept with the vacuum cleaner?
I mean, it's basically the same. If you have it works by filtration. So a cyclone works by the centrifugal force and making the inertia of the particles settle out. They settle out because of their inertia. This is filtration. It's just filtering the dust out. So it works the same way as a similar concept to any filter. And you see these little collection bins down here. So sometimes they'll get really overloaded and the dust just doesn't adhere to the side, so it'll fall out and it gets captured into bins. That's another so combustible dust issue. What if your ventilation system captures a spark that stays live until it comes in here? That's not a good thing. Yeah, you would want. Yeah, so one thing you can do is you can have a spark arrestor that will prevent them from reaching here. I don't know exactly how they work, but another option is to make sure this is outside of the building, and this is, so that won't prevent the explosion, but at least it will prevent it from hopefully, killing people. And another option is what's called a blast door. That's, again, it doesn't prevent the explosion, but it sort of directs the energy. So there will be a door somewhere in the baghouse where if there is an explosion, that door will open to release all that pressure in a certain direction, hopefully outside of the building. Yeah, depending on the factory. But if they generate lots of dust, this is a pretty common, I don't want to say the most common, but pretty common method for cleaning air in industry, at least of particulates. I guess, so real quick, we haven't talked about, after spring break, we'll talk about the theory part of gases and vapors. It's not a lot, but I'm just going to lump it with the respiratory protection lecture. But if you want to clean gases and vapors from an airstream, there are different ways you have to do it, because a fabric material filter is not going to stop CO2 or CO or any gas. It's just going to keep going. So we'll talk about some things like activated charcoal in the gases and vapors, but that is a method for cleaning air. It's the charcoal basically just absorbs the gases from the air, so they stick onto the charcoal, and after a certain amount of time, then you've got to change your charcoal out with a new batch that doesn't have any gases stuck to them. Another option is it's what's called a actually, wait, that's for particulates. There's I'm forgetting what it's called, but it uses a liquid like water, for example. So the air stream enters this location. I'm forgetting what it's called, but anyway, it's got this interface media that helps the water and the air interact, and basically the water absorbs the contaminants from the gas, and then you remove the water, and then you have clean air.
Can I ask a question about
Yeah.
this? Can you run me through how this works again?
Yeah, so this is where you'd have your
Yeah.
butter flavor, popcorn flavor.
Yep.
And so this is the hood. It's capturing the contaminants from the, hopefully from right at the source. Transport it through ductwork could look differently. You have an air cleaner. So depending on what you're doing, you don't necessarily want to, say, exhaust your butter flavor into the neighborhood. Or, you may need to clean the air up before you put it outside.
Tell me if I have this wrong. The stack is where you get the outdoor air. The fan.
So you're thinking of like supply or like an HVAC system. So with exhaust air,
Sucks it up.
so the fan with an exhaust ventilation system, all we're doing is think of exhaust in your car.
Yeah.
You're not trying to add clean air to the exhaust.
Yeah,
You're just trying to get it out. And so that's basically the idea here is you're just trying to get this stuff out. This is nasty stuff. You just want it out. Depending on what it is.
Break in the system?
I don't know why that's there.
Okay, so it's not
It would be, yeah, it would be all enclosed. I don't know what that is, but yeah, so depending on your contaminant, you may want to clean it before you emit it into the neighborhood or whatever. So you'll have some sort of cleaning device. Then the fan is the fan is the workhorse. It powers the whole thing. They're expensive and they use a lot of electricity depending on what type you have. We don't get into the details in this class, but anyway, the fan, it's like a pump. If air moves like fluids, the fan is kind of like the pump. It's like a pump. There are different types of fans. This is showing an axial fan, but actually, I do have a centrifugal fan I should have brought in just to show. But anyway, maybe we can, if there's enough time, on the way to the chemistry lab. But anyway, it'll push it out, and you'll have a stack or something to emit that. You don't. And you want to be careful where you put your exhaust.
Is that regulated by the EPA typically?
Depending on what you're emitting, but yes. I mean, there could be things you emit that aren't regulated, but generally you're going to have to worry about what the EPA thinks of
There was a huge
what you're
glass
doing.
factory in Oregon, and they discovered they were like 2 blocks from a kindergarten, something like that.
Huh.
And it was discovered that they were blowing out massively toxic fumes, and they've been doing it for 20 plus years.
Wow. Yeah, we'll talk more about that with environmental health, but yeah, I mean, a child population is going to be more susceptible than like a working adult population. So people who work, for example, in the factory probably have a stronger or more robust immune system and just resilience to the exposure than the rest of the population. They call that the healthy worker effect. Sometimes companies they might do a study and they'll show, like with epidemiology, and they'll show that their workers have lower cancer rates than the general population. That's probably because of the healthy worker effect, that anyone who works here has to be healthy to actually do the job. And so generally they're more healthy than you know, in the rest of the population, you're going to have the two tails of the distribution, the super, you know, unhealthy. And anyway, it's kind of skewed. So different types of hoods. This is common for welding and I mean, not just welding, for other types of contaminants. This would be an external hood. So it's not enclosing the process. An enclosing hood at least somewhat encloses or completely encloses the process that generates the contaminant. So this is a chemical fume hood. This is what we're going to be doing for our lab later. Okay, I forgot that we did have these on here. This is an example of a bag house and then a cyclone, what they might look like. Don't worry about these others. And those are all particulate focused. I don't know why I don't have any that are gases and vapors, but centrifugal fans are considered the industrial workhorse of ventilation. They're usually more effective, depending on the type. They may also be really, really loud. The fans, they you know, there's just, if you can eliminate or substitute hazards, then you don't have to mess with fans and ventilation. But if you do, then you got to deal with paying for the fan and the electricity and dealing with the noise that it creates. So, but don't worry about those. Axial is, you know, kind of like a propeller blade on an aircraft. Because of time, we won't review this in depth, but just remember, flow equals the velocity multiplied by the area. And with what we do today, you'll be able to estimate the flow of the fume hood that we're going to measure. So we're going to measure velocity. We're going to measure face velocity on a fume hood. We're going to look at what the recommendations are for that. We'll also know the area of the face, so we can estimate then the flow. So we won't worry about that, but it's in the slide if you want to review that. The dilution equation is the only equation we'll do from today's slides, because I want to make sure we talk about the lab more. We'll do it over here for you guys. I want to try and be spread this out. So I think, yeah, the original equation doesn't look exactly like this. I modified it slightly to make it simpler. It usually has a negative sign, and these two numbers values are flipped. But if you just, with the way logs work, if you flip them, then it's the same number, it's just positive. So you can remove the negative sign. I don't know if that was a good thing or a bad thing to do, but it makes it slightly simpler. And you can think of this in the change in time, where it's the time it will take to dilute a certain environment from one concentration to another. So C1 would be the concentration you start with. So let's say that you, well, I mean, let's think of the printing lab, the 3D printing lab. And let's say we assume that, you know, we saw that it's not well mixed, but let's say that 5 parts per million of VOCs have sort of dispersed themselves evenly across the 3D printing lab. We could use this equation if we had a fan. So we do have a fan that looks kind of like this in the lab. If we had this fan and we know its flow rate, so usually that's how fans are rated. One way that they're rated in different ways, but one is the flow that it will generate. If we know the flow and we measured the room and we know the volume, and we started with 5 parts per million, and let's say our target is 1 part per million, then that would be our C2. So the volume of the room would be here, our flow rate here. As long as the volume and the volume in here are the same, then you don't have to worry about units. So if it's cubic feet and cubic feet per minute, then you don't need to do any conversion there. Just make sure that you're aware of that. And if these two concentrations are the same, don't worry about the units because they'll take care of themselves. But so 5 parts per million and 1 part per million as an example. Then we can figure out how long it'll take for that fan to reduce the concentration by dilution.
So I'm not really sure how to go about this.
We're going to do it right now.
No, I mean on the calculator. Is it log or an LN?
Natural log. Did we didn't talk about logs, did we?
Nope.
Real quick, if I say log 100, if I don't put the number and it says log, assume it's base 10. And if I ask for that, what I'm really saying is, what I'm saying is 10 to what number will give me 100? If I say that, if I say log 100, what is the answer? What that really is telling your translating it to your own, to English or something easier to understand. 10 to what number will give you 100? And what's the answer to that? 2. So if I punch in log 100 on my calculator, it's going to give me 2. So that's what it's asking. Log to what number is going to give me, excuse me, 10 to what number is going to give me 100? So natural log is the same idea. It's just a different base. I'm gonna erase this. It's 2.71828. You don't have to remember that, but that's the base of a natural log. So if I say ln 6, I don't know. That means 2.7 raised to what power is going to give me 6. I was trying to go with 2, but I don't know what 2.71828 squared is. What is it? It's probably like 7 or something. Oh, yeah. What is ln 6? Okay, I was off. Obviously, it's probably more like 8 or something, but 7.389. So, yeah, ln 7.389. Yeah, it'll depend on your calculator, but some of them will. If you hit ln, it'll give you the open parenthesis. Then you need to put the number close parenthesis. Some you may have to enter the number first, 7.389, and then hit ln. So let's.
Wait, what was the answer?
For what? The ln 6. It was 1.7, I think.
1.79.
Yeah, something like that. Yeah, you got it. All right, so let's pull out what we need here. We are C1, so after a busy week of printing, the concentration of VOCs is 50 parts per million. So that's our C1 is 50. So that's a lot more than we saw. This is probably not our printing lab. The room dimensions, so our volume is going to be 50 by 50 by 10. So we're going to need to do that math to get the actual number there. And our final concentration is 10 parts per million. Our flow, hold on. We're using this number as our flow. So we're assuming that there's a single round duct supplying air to the lab, and the flow is 173 cubic feet per minute. All right, so how long is it going to take in minutes? So T equals what? So we have something like you're ahead of me. I think it should look something like that. And then 232 minutes.
What's that, 50/10?
Yes. Is everyone able to do that? If not, it's okay. Let me know. And we'll look at it. Well, so I gave it to us. I gave it. It was on a previous slide. It's a 2 or 3 slides back. So 230 minutes. So what is that in hours? Almost 6 hours, right? Or I'm off. Yeah, why am I off so bad? Wait, 232 minutes. I don't know why I did this number in my head. Don't trust this number. 50 by 50 is 2,500. And then and then by 10 is 25,000. Okay. Let me see here. You have a graphing calculator?
Then you should do log 5, right?
Yeah, it'll be natural log 5 times.
Yeah, 140.
Yep. There you go. All right. I'm going to talk about air change rate. We won't talk about capture velocities. Just know that further away you move from your hood, the less velocity you're going to have because it's spreading out over a larger area, just like your thumb on a hose, for example. The air slows down. So you have to be aware of that. So just some quick things to look for if you're evaluating ventilation. Some things that are bad generally is lots of branches coming in or out. Now, if it's designed appropriately, then that's not a problem. But a lot of times what happens is you'll have a duct that is exhausting air at, say, 2 workstations, but then they want to, operations wants to install 3 more workstations. And rather than change the fan and the ductwork, they'll cut holes in the duct, add in extra hoods. And then you're sort of, if you remember Q equals VA, and the flow of your fan is going to stay the same if you don't change the fan. If you've added, let's say they had 3 workstations and they just added 3 more. What have you done to the area? You've just doubled the area that your ventilation has to ventilate. The system has to ventilate. So your velocity is going to go down by, double. It's going to be cut in half. So you might not have enough velocity to capture stuff. So that's where if you hold the paper on the hood, you'll just see this little weak. And if it's a carpentry shop, that's doing 0 except wasting money to make the fan run. So It's just wasting money. So that's where, you know, you can save a company some money. Lots of elbows are bad. If you think of nice smooth flow in whether it's water or air in a pipe or a tube, the more, or if you're on the freeway, you know, the more curves you have, the more you have to slow down. And the sharper the curve, the more you have to slow down. And if you're in a bunch of traffic, you have to slow down a lot because so you don't run into each other. So that's bad. Flex duct is convenient, but all those ridges make it hard for there to be nice, smooth flow. Lots of hoods, especially if they're put in after the fact, that's bad. And some people, sometimes they think bigger is better. And so they'll want to have a massive hood, like a face, but that's not always better. Just like when you put your finger on the hose, you want to increase the velocity so you can at least capture the stuff. And so sometimes smaller, a lot of times smaller is better. Flanged hoods. So that slot hood I drew before, this is unflanged. What a flange looks like is it's like you put a thing around the outside of it so that there's the contaminant can't go around the backside of the face. You reduce the number of options, you know, for flow. Yeah. So this is flanged, although this doesn't look very good. You can see like just how many curves and elbows are here. I don't know. It looks kind of messy to me.
What's a flange?
It's just like a plate, a metal plate you put around the opening, like this. It limits, airflow. If a contaminant is approaching here,
Limits it from going around.
right, there's the option to go around, so it increases the efficiency a little bit. In closing the process, you want to pull air away from the worker. You can see this one is just pulling it to his face. That's bad. So one of my classmates and friends from U of A was doing work at a fume hood. Now this was before I met him, but he was doing work at a fume hood, and he can't remember what chemicals he had. I think like nitric acid or something. Anyway, he was doing the work and he realized he was starting to get kind of lightheaded. But before he could do anything about it, he had fainted from exposure at the fume hood. So overexposure does happen. Now, luckily he was okay, but it's important that you keep in mind some things. Now, we're going to be evaluating the face velocity, but you also want to look at other things that are going to obstruct the flow in the fume hood. So it's not a storage hood. There shouldn't be a bunch of stuff stored in there because that's going to mess up the flow of air. So that's something to look for. That's not face velocity. So we're going to measure face velocity. Now, it's a big opening, so we're going to take multiple measurements, and we want to make sure that no one quadrant of that face is more than 20% off from the average for the whole thing. So those are the two things that we want to reference in this after we measure the face velocity. If it meets these things, then we're good. If you've got a lot of variability, that indicates something might be wrong somewhere in the system or with the fume hood. And if it's too low, then like that one slide said, the table 60 to 100 is what you want for gases and vapors to capture them. Not to transport is super easy, but to capture them, you at least need, you need something 60 to 100. So the basic procedure is we need to divide. We have to divide the face of the fume hood into quadrants or rectangles. We have to measure the velocity at the center of each of those quadrants or rectangles. And then we test with the sash open to 100% 50% and 25%. So what we're going to have is, and that's just saying what I, so assume we have a chemical fume hood that is 48 inches wide by 24 inches tall. So this is from here to here, it's 24. From there to there, it's 48. We have to, these are imaginary lines, like we can't draw lines in space. But, well, I guess string might not be a bad idea. What we have is, one thing we can do, well, we're going to do two things. Oops. So this probe has measurements on it. And what we'll do is we'll measure on the fume hood itself and put a little tiny mark with pen across the bottom. So for example, we'll take our measurements, then move to the next one, take measurements, move to the next one. It's important that we don't get in the way of the face, because that will obstruct the airflow as we're taking the measurements. So we have to try and stay out of the way. But if this was 24 inches and we have these four, what's 24 divided by 4? If we have 4, 6. So each of these is going to be 6. Each of these rectangles is 6 inches high. That means, so we're not measuring at that point. We have to measure in the center of the rectangle. So that means we'd come up 3 inches, and that's where our center line would be. And then we've got to do the other way to figure it out for the other dimension. Does that make sense? So we're not measuring where the rectangle lines are. We're measuring in the center of the rectangles. So this is assuming 24 by 48. That's to give you an example. The fume hood up there is 26 by 64. So 26 tall by 64 across. So in your teams, why don't you, I don't think so. So Dr. Eaton is going to let us in. She won't be in class. I think she's the one who usually, this is the OChem lab. She's the one who typically uses it. And I mean, she said we could go in there. So I assume that there won't be a class. She didn't say there would be, but if so, then we'll try the biology lab just next door. There are 2 or 3 labs that have fume hoods in there.
Isn't it Jesus building or stuff?
In STEM. So maybe we could have sort of half of you work on the height dimensions and the other half on the length dimensions. Just
Or you can paint. Or you can paint.
So it's with the 64 inches. So you're gonna do 80.
so I'll be back in just a couple of minutes. All right. Really, if you find this dimension, then you just have to cut it in half and then add that same dimension to itself each time it goes. Does anybody have their dimension done?
Yeah.
Let me mic up real quick so it's on the recording. All right, do you have height or width? Okay. All right. Let's go with the height first.
So the first dimension, 3.25.
So maybe I'll do it over here so that it 3.25.
9.75.
Okay.
16.25. And then 22.75.
So you probably can't see that, but so they would be these numbers here.
Yeah, I get that, but why wouldn't it be 3 inches to the first one? I
Because,
don't
well,
understand what you're
it's not
talking
nice and even because it's 26. That the actual fume hood is 26, not 24. If it was 24, it would be.
All right, I got it.
It would be. I use 24 and 48 because they're nice, easy numbers. But reality usually isn't nice, huh? So, all right, let's get the others from somebody else. Who has the width? Yeah, go on the other way.
8
Sorry, just
inches.
8. Okay.
24.
This- So this one did work out because 64 you can divide by 4 nice and evenly, thankfully. All right, so those are the dimensions. 2 groups aren't going to be able to take measurements. I'm sorry. So I need 3 groups to volunteer to help with taking the measurements and the others to observe. So 2 groups are just going to be observed. Or I guess smaller groups could combine if you want to be involved in the process. You don't have to be. But I had mentioned 100%, 50%, and 25%. So and maybe this is a group that could kind of double up. One group is going to measure all 16 rectangles with the sash. So imagine this is the face. You're going to open the sash all the way to the, basically as high as it'll go. And it might alarm, and we'll silence the alarm like we shouldn't do. Because the face velocity is going to drop below what it's supposed to. That's why it's going to alarm. But we're doing a test, so we're not actually using any hazardous chemicals. So the first group is going to open it all the way and measure all 16 points. The next group is going to only go 50%, so that would be to 32 inches. So you won't need to worry about the top 2 rows. You won't have to do those. You'll just do these 2 bottom rows. And then the last group is going to do it at 25% open. So that means you're just going to do this bottom row. And you'll notice, you'll be able to see, and this is something, if anyone wants to go the extra mile or they're just nerdy like me, in your lab report, you could do a scatter plot of the relationship of the area to the velocity. And you'll see that as you'd see something kind of like this. I mean, in theory, it would be a nice straight line. It might, be something like that. But you could just observe how as the area decreases, so we're going to start over here. We're going to have a point over here. Or no. Wow, no, yeah, that's right. As we have a large area, then the velocity is going to be lower. And then, as we close it down, I guess we'll only have 3 points, but anyway, then you'll see that how it increases there. So what might a recommendation be for students who are using the chemical fume hood? Yeah, so keep the sash height down and just a little opening, just enough for you to do your work. Did you have a question? It looked like you were going to ask a question.
Yeah, this should be exponential. I don't think that relationship. As the area increases to infinity, your velocity goes to zero. As your area goes to zero, your velocity increases.
You may be right. I'm just thinking of the equation. I guess, yeah. For some reason, I was thinking of the equation Q equals VA, where if your flow stays the same, then, so you may be right, but I guess I can't say for sure. But you should see some nice sort of relationship there, either linear or, well, I guess between our 3 points, if we just did them, it might look linear, but if we plot them correctly, then it probably wouldn't look linear. I mean, if we, 25, 50, 75, we won't have a 75 point. But anyway, that's kind of beyond the scope. All right, any questions? I'm going to move it back so that it's after. Yeah, and just in general about the class, not just the exam, but if I need to curve things or do something else, I will, but I'm going to wait to decide on that to see how you guys do. Anyway, so what is there any group or groups that want to do the full? They want to split the 100% open.
You can go first.
Okay, you guys are. What's your name?
Green power.
Green Power.
Green power.
Green Power. Okay, Green Power. I need one other team to volunteer to do. You guys? Is that BJ? Okay. All right. So Green Power and BJ are going to do 100%. I need a group to volunteer for 50% open. Let's see. We have Bull, Prestige, Purple. Is that it? Oh, we have one more. No, we have 5 groups, right? Bull, Prestige, and Purple. Prestige? Okay. Prestige is going to do 50%. I need one more for 25. For the group that doesn't get an assignment, I guess I'll say that it's your job to make sure that everything's on the discussion page on Canvas for this, for anybody who missed.
I'll take care of this. I can't take over for a while.
Okay. Okay. All right. So Bull Inc. We'll just make sure that data gets posted. Sorry, I didn't even think about that. But
That's why I was curious if it's gonna be in lab or not.
yeah.
Regardless.
Okay. Fair enough. So then that leaves purple. You guys do this then? Measure the 25%. All right. So we'll head on up there. So it's the second floor of the STEM building. I am going to go straight to Dr. Eaton's office to grab her so she can open it for us. But you guys could meet at somewhere on the second floor if you don't know exactly where the chemistry lab is. It should say it though on the door.
So when is this lab due?
It will be 2 weeks from this Wednesday. So it won't be due during spring break. You won't have anything due during spring break. So yeah.
So
Yeah.
the 20th,
Whatever that is, that sounds right.
the first week that we're back.
The first week after spring break, yes, on that Wednesday, it'll be
But
due.
we still have a quiz during.
That will be moved as well. There's no point in you doing it then. I'll do it so it's on the same day as lecture. So you can come back and do the quiz that same day if you want.
I was going to ask about the poster. You won the 6th. Are we going to present it on the 15th, right?
Yes. Yes.
Can you postpone it to the 8th, for example?
Well,